Hello, everyone. Welcome to this journey into time series analysis with tsbootstrap. This presentation unveils the capabilities of this library. It's a cutting-edge Python library that transforms the way we approach bootstrapping for time series data. We'll explore the various innovative features that this library offers and what makes it stand out in the realm of data science. The agenda will be something like this. We'll start with explaining what time series is, the specific challenges of time series, why traditional bootstrapping methods don't work well for time series data. Then I'll overview some key techniques implemented in tsbootstrap, like Markov bootstrap, residual bootstrap, block bootstrap. I'll demo the library functionality quickly, and then we'll finish with takeaways for using tsbootstrap in your own work. So let's start with a simple analysis, right? What is time series? It's a sequence of data points collected over time intervals representing change of variables. So essentially you have two columns. One is your timestamp, two is some variable. Analyzing time series poses unique challenges, namely autocorrelation, where data points are correlated with their past values. This complicates traditional methods of analysis. Non-stationarity, where statistical properties change over time. This could be mean, variance, kurtosis, what have you. This adds another layer of complexity. Analyzing and addressing these challenges is crucial for accurate forecasting and understanding underlying patterns, and which is why time series analysis is usually a separate topic in and of itself than traditional IID data analysis. Well, the library is called tsbootstrap, so it stands to reason we should start with understanding what bootstrapping is. I'm sure everyone here already knows, but just as a quick refresher, bootstrapping refers to resampling your dataset with replacement to approximate the unknown sampling distribution. It's commonly used for obtaining confidence intervals, for model validation, for hypothesis testing. Classical bootstrap assumes IID data, which, as I explained earlier, is ineffective for time series data. So assume you have time series where the timestamps, they go from 1 through 16. Pardon me, 1 through 15. It's a 15-unit long time series. This slide visually represents or demonstrates what regular IID bootstrapping looks like. So here I have 3 draws. If you look at the very first row, where I've highlighted with red arrows, the timestamp or the index 5 repeats 3 times. The index 1 repeats twice. Similar things happen in the other 2 draws also. The reason for this is to highlight that bootstrapping, the way traditionally the term bootstrapping is used, it refers to resampling with replacement, replacement being the key term. Oh, there was the next slide. There we go. Why does classical bootstrapping fail? Well, the key issue is that classical bootstrapping, it disrupts the temporal ordering of observations in time series data. So you end up destroying the inherent autocorrelation structure. You start treating your data falsely as IID, which breaks all statistical assumptions that are required for validity. The arrow of time really goes in one direction. So you can't, as you can intuitively think about it, you can't just jumble up those indices or those timestamps ad hoc, as you would be able to do for classical or traditional bootstrapping. This library implements several bootstrapping methods. In this presentation, I will focus on 2 of these, block bootstrap and residual bootstrap. Block bootstrap is the most common bootstrapping method used for time series analysis. So we'll spend some time going over it. Whereas residual bootstrap is, along with, say, other methods such as markup bootstrapping, sieve bootstrapping, which are included in this library, are a little more advanced technique. Residual bootstrapping is a little more advanced technique, but it gives you significant more flexibility depending on the kind of time series data you're dealing with. So block bootstrapping, as you can see on the left side, here we resample blocks of consecutive observations rather than individual points. So you chunk up indices together, and then you resample with replacement. What you end up doing is you end up maintaining short-term chronological integrity. The key, as you can then imagine, is selecting the appropriate block length to trade off bias and variance. This method, this library gives you other methods like residual bootstrapping, where instead of resampling the original time points, you fit a model to it. You get the residuals, and then you resample those residuals. Not shown here, but included in the library are markup bootstrapping, sieve bootstrapping. Markup bootstrapping assumes that the residuals, they follow a Markov process with limited memory. So you take your original time series data, could be univariate, could be multivariate, you fit a model of your choice. Could be something simple as ARIMA, could be a really fancy deep learning model. You get residuals. And if your assumption is that the residuals follow a Markov process with some limited memory, then markup bootstrapping would perhaps be the right choice for your case. Here we resample the residuals rather than the original series, like I mentioned, in which way we end up preserving both the marginal distribution and the short-run dynamics. Another method that's presented in the library is sieve bootstrapping, which is a semi-parametric approach similar to residual and Markov, where you capture long-term temporal dependencies by fitting an AR model, autoregressive model, to the time series before resampling the residuals. Now, with this sort of high-level overview out of the way, we can spend some time really understanding what block bootstrapping is. Like I briefly mentioned, this is the most popular type of bootstrapping. The TLDR is chunk up your time series data into blocks and then resample the blocks. This library allows you to significant flexibility in the way you can select the block length. The user can provide a fixed block length, or he or she can provide a distribution from which to draw the block length. You have flexibility in how to overlap two blocks. We're going to look at that. You have flexibility to assign different weights to different points in each block. You can say the center of the block is much more important than the edges, so you can have a tapering function. Or you can say the start of the block is much more important than the end. So that comes later. That's just a sort of a prelude. Block bootstrapping, as you can see here, is instead of fiddling with individual points, we shuffle whole blocks of data while keeping their order and autocorrelation structure intact as much as possible. There are 4 main types of block resampling strategies in literature and also implemented in this library: moving block bootstrapping, stationary block bootstrapping, circular block bootstrapping, and non-overlapping block bootstrapping. What makes block bootstrapping stand out from classical bootstrap is its ability to preserve time dependencies, at least in the short term. It is the go-to for many people for time series data. Plus, it's a cinch to compute, and it's lightning fast. So in short, block bootstrapping is a building block for more advanced bootstrapping techniques, and it helps us make sense of time series data with more accurate and valid inferences. So that's a lot of talk. Let's look at something visual. Again, recall that my time series indices are 1 through 15. And I have 3 draws. You'll recall from a previous slide that we drew individual points, but here, like I mentioned, we draw blocks. Before drawing blocks, the first step would be to actually create those blocks. So here I've specified a block length of 3. Moving block bootstrapping allows you to start from anywhere in your time series data, and you still resample with replacement. So in draw 1, you'll see blocks consisting of indices 1 to 3 are repeated. This is similar to the repetition I showed earlier. Similarly, in draw 2, blocks 7 through 9 are repeated. Moving block bootstrapping is used for time series data where blocks are resampled to maintain dependency structure within the blocks. It's specifically useful when data has dependencies that need to be preserved, and I would not recommend this when the data does not have any significant dependencies. Circular block bootstrapping. If you notice the last slide carefully, you'll see that we didn't ever go back from index 15 to index 1. However, circular block bootstrapping allows one to do that. This method of block bootstrapping, it treats the data as if it is circular, i.e. the end of the data is next to the beginning of the data. It's useful when your data is cyclical or seasonal. And of course, it's not recommended when the data does not have a cyclical or seasonal component. So here, via arrows, I've tried to point out those specific blocks. So 15 to 2 in draw 2, you start at index 15 and then you loop all the way around to 1 and 2, while keeping the block size of 3 constant. Same thing in draw 3. We start at 14, we go to 15, and then we go to 1. The second we reach the block size of 3, we stop. Another thing to note is right here. If you notice block 6 and 8, and block 7 and 9, there is overlap. By default, the way circular block bootstrapping, moving block bootstrapping are defined in literature, there is an overlap. However, I allow the user in the library to set what this overlap needs to be, to hard code a value or to set a min value, a max value. If they don't want any overlap, they can also do that. Stationary block bootstrapping randomly resamples blocks of data with block lengths that follow a geometric distribution. So the idea here is that the block length isn't constant, but it's drawn from a distribution, and that distribution is a geometric distribution. It's useful for time series where the degree of dependency needs to be preserved, and it doesn't require strict stationarity of the underlying process. It's not recommended when the data has strong seasonality or trend, which violate this weak dependence assumption. Again, via these yellow arrows, I've pointed out those blocks where block lengths are greater than the, you know what, ignore the third draw because that's an error. Just if you could focus on the arrows in the first 2 draws. I'd given a block length of 3 as that is a parameter of the geometric distribution. And in this draw, one of the block lengths is a block of just a singular value, number 3. This is index 5. So this is easily allowed or can easily be achieved in this library. I've extended this functionality where the user is not restricted to drawing just from a geometric distribution. If you know or if you learn that your data, the blocks, there is they're drawn from some other distribution, you can pick any of the ones allowed by SciPy. So that's easily doable using this library. And finally, non-overlapping block bootstrapping, as the name clearly implies. Here we resample blocks of data without overlap. It's useful specifically when your data has dependencies that need to be preserved and when overfitting specifically is a concern. If the data does not have significant dependencies, or when the introduction of bias due to non-overlap selection is a concern, then perhaps non-overlapping block bootstrapping is not the best for you. If you notice closely, there is literally no overlap in any of the blocks. However, there is still repetition. So for instance, blocks 1, 2, 3, 1, 2, 3, 7, 8, 9, 7, 8, 9 are repeated. And in all these draws, you keep on drawing blocks until the length of the new time series equals the length of the original time series. This is my favorite. Okay, so here, now that we've covered block bootstrapping, we're going to move on to the other sort of building bootstrapping method that's allowed by this library, called residual bootstrapping. And I wanted to, again, demonstrate visually when and why this method would be useful. So the blue line is your original time series. This is y equals to x plot. You go from index 1 through 15. Now, let's say if I follow either IID bootstrapping or block bootstrapping. In this example, I've followed block bootstrapping, where in my first draw, I draw samples 1, 2, and 3. That's my first block. Pardon me, we're looking at the y-axis. So we draw samples 9, 10, and 11. This is our very first block. Second draw, we draw 7, 8, and 9, and so on. I'm following the red curve here. And then we basically stitch them together in the order in which they're drawn. So this is block bootstrapping. This is moving block bootstrapping. And then we have 2 similar draws. The idea here is, what I'm trying to demonstrate is, let's say if you have even a simple linear trend in your time series data, and you go ahead with moving block bootstrapping, the kind of results you'll get after stitching those indices together, the final time series will probably not resemble the original time series in several properties. Here, for instance, if you look at the yellow one, and if you were to fit a best fit line, it'll be a horizontal line, which means you've lost the trend completely. So this is where we come to the realm of parametric or semi-parametric bootstrapping methods. Specifically, in this presentation, I've demonstrated residual bootstrapping. So this is one of the several model-based approaches that are available in this library. It is a very popular model-based approach. What you do is you first fit a model to the data, and then you bootstrap the residuals. In tsbootstrap, I've provided several statistical models, starting with ARIMA, SARIMA, AR, and some volatility-based models also to deal with financial data. This particular method can be advantageous, as it allows the bootstrap method to take into account the structure of the model. So fit a model of your choice to the original data, get the residuals, resample the residuals, add them back to the fit, and that's your new time series. The difference between the resampled data here and here is, I'm sure you can see visually, quite striking. You maintain the trend. It allows you, this method allows you to handle changing distributions, drifts. Since residual bootstrapping is based on a fitted model, it can better handle situations where the data distribution changes over time. It is better for complex distributions, as the dependent structure is captured by the model rather than by the blocks. It is less sensitive to block size because it does not require choosing a block size, making it just less sensitive or really not at all sensitive to this parameter. It can be more efficient. Depending on the model used, residual bootstrapping can be more computationally efficient than block bootstrapping, especially for larger data sets. With that, all of that introduction out of the way, it was very important to cover the basics, because these are the functionalities that tsbootstrap offers. It is an open source, property tested, not just unit tested. We use hypothesis for property testing, It has 85% coverage currently, and I plan to increase that to 90 by the end of the month. It is extremely flexible, it is very well documented, and it's very easy to use. I provide both basic block bootstrapping and advanced bootstrapping methods, such as residual, which we saw visually, sieve bootstrapping, Markov bootstrapping, distribution bootstrapping, statistic preserving bootstrapping. I encourage you to actually go to the GitHub page or the PyP page and look at the documentation where I've described these methods in some detail and when to use them and when not to use them. What I've also been able to do, because the code is so modular, is for the advanced methods, you can apply them as is to your time series, or you can combine them with the block bootstrapping methods. So for instance, the residual bootstrapping method that we saw earlier, you can fit a model to your original time series, get the residuals, and instead of ad hoc resampling the residuals, assuming they're IID, you can then bring in block bootstrapping, chunk them into blocks, bootstrap them, resample them, add them back to the fitted values, and now you have your new time series. Like I mentioned, it's the table of contents. The README file is quite well documented. I tell you which file or which module, which class each method is implemented in, and there are examples how to use them. It is extremely modular. The code is structured into distinct modules for ease of maintenance and extension. It is enterprise-grade code. It has a very detailed README file, contributing guidelines, usage examples. It follows dry and solid principles for efficient code management. It has excellent CI/CD. It is community-focused and includes a couple of conduct and contributing guidelines to foster community involvement. We already have some open issues. It has a simplified setup and a setup process using a setup script. And we are working to integrate tsbootstrap into skTime. Because of the way it's coded, it's actually very easy. I'm in contact with the devs of skTime to integrate bootstrapping, tsbootstrap specifically, into skTime. What this would allow you is the ability for excellent uncertainty quantification. So if you have your original time series, a black box model that forecasts either one step ahead or n steps ahead, but you're not sure what the error bars there could be, you can take your original time series, create multiple copies using tsbootstrap, feed it to the same model, get multiple outputs, and now you have a distribution. skTime already has a end-to-end pipeline set up for everything except the bootstrapping part, and the synergy is just fantastic. How to use it? It's like I mentioned, it's extremely easy. I follow the config paradigm to keep code very neat. You literally do pip install tsbootstrap. In this example, I've demonstrated how to use moving block bootstrap, and then you import the config. You create an instance by mentioning the block length and the number of bootstraps you want. And then you have your generator, where you can either specify if you want to return the indices in addition to actual values for the variables or not. This was inspired by the way cross-validation and done in sklearn, where they follow the generator paradigm. In the visual examples where I showed you distinct blocks. What's happening here is those blocks are just stitched together in the order in which they are drawn. So you have, if the block length is 3, you have 9, 10, 11, 7, 8, 9, 5, 6, 7, 5, 6, 7. Like I mentioned, repetition is okay, block length is preserved, and so on. And then you have 3 distinct draws. Finally, here's my contact information. Please reach out either on LinkedIn or via email. If you have any suggestions, concerns, feature requests, if you find bugs, definitely open an issue, ping me. And yeah, I think we ended at almost 25 minutes, leaving 5 minutes for Q&A. Yeah, any questions? I'm gonna look at the.
Yeah. Thanks so much, Sankalp. I think there's a question in the Q&A, and there might be a question in chat as well. Let's do the Q&A.
I'm sorry, Arliss, I couldn't quite understand you there.
I'm sorry, I think we have one question in the Q&A. I'll bring it up on screen.
Okay, you're right. You're right. I'm seeing it right now.
There you go.
So Ajay, sorry if I'm butchering that name. Residual bootstrapping doesn't actually, by default, doesn't actually use a distribution function. The block length, I'm guessing you're referring to the block length, is fixed. It's user specified. So you can specify whatever block length. And yeah, that's the, if you combine residual bootstrapping and block bootstrapping, that's the block length right there. Or the other way I can interpret this question is you don't combine block bootstrapping with residual bootstrapping. And then you assume that when you do IID resampling of your residuals, you're assuming they follow a normal distribution, as with IID data. So I'm not sure if that answered it. I answered it from two perspectives. Any other questions?
I think there was a quick one in chat.
You're right.
Are there occasions when you might want to use this property and use MA or ARMA models?
Absolutely, yeah. I provide very convenient wrappers around AR, MA, ARMA, ARIMA, SARIMA, and some volatility-based models. So the choice of which model to use is really up to the user. As a data scientist, MLE, you know, a time series specialist, you do some analysis on your time series, or you get with domain experts, and you figure out what would be the best model to capture the underlying properties of your time series data, and then you go from there. So absolutely, the intuition is right. There are times when MA would be a better fit than AR.